Okay, class, it looks like the author really knew that you were just going to love doing these problems, and so they've given us another one. And if you'd like, I can certainly find you a whole lot more. But we have number 6 here, and we have an airplane flying at a speed of about 100 miles per hour was once overtaken and passed by a flock of sandpipers. Okay, so we have a plane that's traveling, and then you have these birds that are coming, and they actually pass now the plane. Now, suppose that the flock of birds can fly at 110 miles per hour with a certain wind and at 90 miles per hour against it. If they fly a certain distance with the wind and the same distance against it, how far can they fly in all if if the trip takes 2 hours? Okay, our head's spinning again, isn't it? Now, until we start putting the pen to the or the pencil, I prefer pencil. I mean, not say pen, but put the pencil on the paper, and you start drawing this and showing the relationships. It's just going to make your head spin. But there's some buzzwords, things that we need to identify first before moving on, because we're going to create those relationships on our paper. Before we do it, we need to understand the words that they're using, and there's a you have to have a certain level of familiarity with those words and the little buzzwords that are going to tell you, this is equal to that, and this is the relationship of one to the other. Okay, so let's sit there and just take a quick overview of this again, and we're going to take a look and say an airplane is flying at a speed of 100 miles per hour, and it's overtaken by a flock of sandpipers. So we can see this plane and we can see sandpipers. Now, that's really not where our problem is right now. Our problem is actually going to be now, suppose that the flock of birds can fly at 110 miles per hour with a certain wind. Okay, a certain wind, there's a buzzword, and 90 miles per hour against it. Okay, that would be the certain wind. Okay, now if they fly a certain distance with the wind, and again with the wind, and then the same distance against the wind or against it, how far can they fly in all if the trip takes 2 hours? Now, remember the one problem that we did where they were traveling a distance and then it's the same distance, and there was a wind too helping it and a wind against it. So let's picture that, and let's go ahead and just draw. Well, I'm going to be going from this point to, oh boy, my wonderfully straight lines. Just picture that as being a straight line. Okay, and so we have with the wind and against the wind, and here let's just call this with. Okay, I believe they're going to actually want a couple of illustrations here, but this is with and this is against. All right, and we know that the distance is equal, right? When a certain distance, and let's see where we get that. It says the same distance. Really important. That's the buzzword. That's the clue that you really need to solve this. Same distance. There is the foundation by which you're going to build your equation. But we need to get the components. And we do understand that there's a d is equal to RT up here, right? And there's a d is equal to RT here, right? So there's D1 and there's a D2. And we know that D1 is equal to D2. So you see, this is already making you feel a little more comfortable, hopefully. But we still have to decipher some of this information that's being given to us, and it's still you still have to work. There's critical thinking that's going on here. Now, we're given information that the birds fly at 110 miles per hour with a certain wind at 90 miles per hour against it, right? So, let's sit here and determine. And we're also told that the total trip takes 2 hours, okay? So if the total trip is going to take 2 hours, we can then determine we're given at least a bit of information as it relates to one of the components. Now we know that if we were to say if x represents the time, and that's where I was pointing to, the 2 hours is going to be part of this time feature. It says here the trip takes 2 hours. So if x represents the time that the flock spends flying with the wind, so that's this one here, right? With the wind, okay? So that's going to be x, all right? And how much does it spend time flying against the wind? Well, again, let's just pause, and we're saying, well, x is the time that it takes going in one direction, and we know the total time is equal to 2 hours. That's quite simple. I just need to subtract x from 2 hours, right? So this would be 2 minus x, because this is how long it takes to go here, and then this is how long it takes to go here. Well, we know the total trip is 2 hours, so whatever it took here, I simply subtract it from 2, and I can determine here. And we've gone over this. I know sometimes there's just a little weakness in our brains trying to understand that well, it went x distance, and the other one's 2 minus x. Well, again, we did it before. The total trip is 2. First half took x hours, so the second half is 2 minus x, because it has to, the two of them combined have to equal to 2. So, and if we were to take this mathematically and say, well, this is x time, and I'm going to add this to 2 minus x, right? And what do I get here? Well, x minus x is equal to 0, so the answer is 2. So that is the time, right? You see, it works even when we try to do the math. Now, so if our answer to A is 2 minus x, we're going to now use that information. It says draw a diagram showing the distance flown with the wind and the distance against it. Well, what do we know about the rate of the first one? The first one, we had a rate of, I believe it was 110. Okay, so again, I'm just going to write here 110, and we have a rate of x. We know that this is 110 x, right? That's the distance. It's the rate times time. And the rate is 110, and the distance is x. So there you go. It's that simple. We just multiply the two, and that's the distance. You say, well, I don't know what that distance is. Why are you telling me that's distance? Well, it is because we just simply don't know what x is. But we're going to find out what x is. Now, over here on the bottom, what is our rate? Our rate here is 90, right? So we would take 90, and we will multiply it times the time, which we already know to be 2 hours minus the first time, which is x, which is now 90 times 2, or 90 times parentheses 2 minus x n parentheses, okay? So we could draw this illustration. Now the illustration really shouldn't have all this. I'm just the illustration could simply be two different lines that are equal, one showing this and one showing that, but this is what's going on here. This is equal to this, and this is equal to this. And again, the relationship of the same distance. That's what they told us, the same distance. So now let's take a look and say, use the information in your diagram to write an equation. Okay, so we did A, and then we did B. So we let x represent the time that the flock spends flying the wind, and then we found out how much time does it spend flying. That's each, using the x value. Then we drew the diagram to show the distance. So we see that. Now we can do an equation. Well, we know that the top is equal to the bottom. Do we not know that? So we could simply write 110x is equal to 90 times 2 minus x. And again, remember, this is distance 1, and this is distance 2 down here. Okay, and d1 is equal to d2, and we know that d1 is equal to 110x, so we're plugging that in here, and d2 is here. So just trying to show you this from as many angles as I can. Hopefully something is is really just the light bulbs going off, and you can see how the relationship of one to the other is going to help us to determine what the total time was. Okay, and for each, that is. Now, using this, we're going to we have our equation. Now we're going to solve this for x. So our distributive principle is going to kick in over here. We have 110x, do our parentheses. You see how we learned this much earlier, how to handle order of operations and distributive rules and all these wonderful things. And now we're just using, there are all these tools that you're using in math that you've learned before, and you're now using them over and over, which is really going to reinforce that your knowledge. You did a few problems using the distributive rule, but I guarantee you're going to be using the distributive rule for the rest of your math life. And so the more you use it, the more you become familiar with it. That's why I'm not drawing these little arrows as I did before, and I'm just jumping right into it. So now I'm going to add 90x to each side because I want to isolate the x. Okay, so I'm going to add 90x, and just always be careful. Even though you're learning these things, you don't want to just jump and do 2 or 3 steps in one. Could have done that, and I could have made a mistake. Less chance of mistake if you take your time with these and you write things out. So I know this is going to be equal to 180. That's going to eliminate, and that this is going to be 200x, right? So so my next step would be to divide each side. And let's go ahead and do that. Divide each side by 200. And again, you see I just jump into this. Why are you doing that? Well, we're isolating the x. So we divide the 200x by 200, but if we're doing it to one side of the equation, we have to do it to the other. Okay, so it's just that natural process of keeping the equation equal. Of course, it's an equation. It's a natural process of just isolating by using all these wonderful tools that we've been given. And now we're going to come up with x is equal to 180 divided by 200, which is 0.0. Let's just write 0.9. Okay, and so 0.9 is the x value, which is the time. Let's go all the way back up here. What is x? If we look at our x represents the time that the flock spends flying with the wind. Okay, that's up here. Okay, if we look at problem A or letter A and we look up here, that's what the x value is. So now we know that it spent 0.9 hours, which is almost an hour. Okay, we're not looking at this in seconds, and we can certainly have a wonderful time converting that to seconds, or minutes rather, of an hour. But we know it's just quite not a full hour. It's 1/10 of time less. Okay, and if we were to say, well, 1/10 of an hour, how many minutes are in an hour? There's 60. What's 1/10 of 60? It's 6 minutes, right? So we actually spent 54 minutes. Again, that's a little extra. It wasn't part of the problem. But just you can start thinking in terms of conversion of these units. But anyway, let's go back and say, what does it mean then to our last part, solving this for us? How far can the flock fly together? Okay, well, let's go. Well, to determine that, we would simply put in the x value in here, because we know that the flying together meant they traveled the first distance, right? And then they traveled the second distance. Okay, so that's going to be the total distance. All right, that's total, because they're traveling in one direction and then they're traveling the second direction. So that's d1 plus d2 is equal to the total distance, right? So the first distance and the second. Now what's d1? Well, d1 is, let's see, 110 times let's put 0.9, and then plus 90 times 2 minus 0.9, right? So these are the d1 and the d2, distance 1, distance 2, and we're able to plug in now that 0.09 as the x value. And just note that over here, um, the 2 minus zero point 0.9 is going to reveal us our time here. So we're going to 110 times 0.9, and we're going to do that over here. So that revealed the time, and that would be 1.1, would it not? Okay, and that's going to be equal to the total. I'm sorry, that should just be dt. Let's call it. Okay, and you'll learn how these fun little notations that we make on variables, just so that we know what that variable means, because we're using d, but we're using it a couple times here. So d1, d2, and dt are 3 different distances. So let's go ahead and do our math. And if we take our calculator, and I'm just going to take my calculator right now, and you can pull yours out if you want, and we're going to multiply 110 times 0.9, and that's going to give me 99. Okay, so this is 99, and that would be, I believe we're using miles, right? So let's just call this miles. And then if we do the math, now you should automatically know that the other one's going to be 99, right? Because it's the same distance. But let's just double check our math here and say what's 90 times 1.1, and I get 99. Hey, that means we must be on the right path here. At plus 99. So it means that each distance was 99, but they didn't ask us what the distance, the first distance. They said how far can the flock travel together? Oh, I think they can fly as far as they want. But in terms of how far did they travel here, it was 99 plus 99, which is 198 miles. Okay, so in 2 hours, they traveled 198 miles. Now, granted, I'm using the equivalent, the same distance. They could have actually traveled 2 different distances, okay? But they said they were the same, and I used this illustration like they didn't necessarily have to go from point A to point B and back to point A. Notice I didn't use point A and point B, but I did use this as a model for us to show how they equate to each other. What we could have done was drawn 2 different lines, but they were exactly equal to each other. Okay, because I don't believe. Well, it looks like they did. I'll take that back because we're using the wind here as a factor, and it's not to say that the wind could have shifted, but let's just say. So they travel for 1 hour with a certain wind at 90 miles, and then or at 110 miles per hour with a certain wind, and then 90 miles per hour with the wind against it. But again, they don't call this sort of a round trip, and that's irrelevant. But I'm just showing you that the distance 1 and distance 2 were equal because they said it was the same distance. So I just wanted to put a little footnote at the end. It didn't mean that they ended up at the same point. Could have been that wind shifted and they had wind for it, and then you could walk a mile and you can have wind in your face, and then all of a sudden wind's to your back because the wind is just shifting. So again, what we're trying to do here is just understand relationships, understand one thing is equal to the other. The foundation to our problems here are distance is equal to rate and time. The foundation that we're taking from that is that if we're given information that says this is equal to this, beyond that, because we know distance is equal to rate and time, but now we're saying this distance is equal to this distance. So they've given us a clue. There's a clue there. So I know if I can figure out what this distance and rate by rate and time and this other distance by rate and time, I can then put them together and create an equation. So that's really what we've learned here, and we're not going to be doing a lot of these distance, rate, and time problems throughout math, but it's important to understand what it takes for us to do these types of problems, and you may end up using them much more further down, particularly in your sciences, and most certainly if you take physics. Physics is all built around laws, and then they build off of all these relationships, and they use a lot of substitution, and it's just it's an amazing world if you're interested in math. but it's also one that is not as difficult if you take it apart and you look at each individual component and just work your way across. It's like writing a book. If you love writing, you know you're not going to write a book all in one sitting. You're going to probably think of what would your plot be, and I'm not much of an author or writer, but I understand that they try to build the plot, and there's certain elements within, and there's a formula even to writing a book, and you have I believe there's conflicts, and then there's sub-conflicts, and then there's a major conflict, and then in the end, everyone lives happily ever after, or if that's the way it ends. But there's a formula, and they follow that, and they start by writing these ideas and thoughts, and then they slowly start building, and they start building sentences into paragraphs, and paragraphs into chapters, and then they start stringing the chapters together, and then they go back and rewrite it. But my point is that you don't just sit there and write a book from beginning to end. You take it apart and piece by piece, and you put it all together, and that's how math is as well. So there's a lot of relationship in words to numbers, and as we've seen in this particular chapter, we've taken words that are giving us some description, and we're now able to analyze it and come up with information that we were not given. We were given information, but there was information hidden in that information. And in the end, just by knowing that a group of birds were traveling at a certain rate, and it was equal to a certain distance at another rate, we were able to determine exactly how far they went based off the rates that they were given. So it takes a sharp mind to be able to do that quickly, but it's not difficult if you do it little by little and then build your ability to do these things. So that's the end of this particular chapter. When we move into our next chapter, it's going to take us a little bit back. We're going to go back into some other things that we've learned in the past, such as the area, and we're going to go into graphing as well, but particularly we're going to be going into equations with two variables, and now that may sound a lot more challenging. Well, it's okay. Trust me, these are not very difficult if you take things step by step, but you've come this far and you've been able to build a certain amount of knowledge that's going to help you in the subsequent chapters. But this is really the true beginning of seeing algebra in its in its full use, particularly as it relates to those problems that would relate to our world around us. So, and this is the end of your chapter 5.